Hi everybody, welcome back to the Feynman technique. Um, Today we're going to be solving this integral, and if you watched my previous video, you'll see that it is very similar in structure to the integral I solved in that video. This video is not going to be as long. I will link to to the previous video if you want to see where some of the formulas in this come from. But the only thing that will be required to solve this integral in this video is knowledge of calculus BC, um, the Leibniz rule for differentiation under the integral sign. Of course, that's the cornerstone of this entire channel. And some basic complex numbers and taking the real and imaginary parts of them. Actually, this actually will not require the use of complex numbers. I apologize. Um, in the last video, I got quite a few comments saying that the integral was very easy to solve. However, that assumed prior knowledge of the zeta function. And on this channel, as you know, I tend to shy away from things like that, as those things typically aren't covered in a standard calculus BC class. Again, this channel is meant, all the integrals on this channel are meant to be solved using only a knowledge up to calculus BC and some basic complex numbers. So let's get started. All right. So first, I want to rewrite this using um, the exponential definition of cosine hyperbolic. So cosine hyperbolic is just e to the x plus e to the negative x over 2. As you can see, we get the exact same thing. And then I'm going to bring this 2 outside. All right, next, we'll let x equal natural log u, implying that dx is equal to 1 over u du. Plugging that in, well, if x is infinity, you would have to take the natural log of infinity to get that, so it stays infinity. This one, if x is 0, you'd have to take the natural log of 1. All right, so this part right here is just going to become natural log u to the 4th. This is going to become 1 over u. This is going to become u. And our dx is just going to become 1 over u du. And as you can see, this perfectly matches what we expected to. So the substitution was performed correctly. And then I will distribute this u downstairs. So we just get 1, and then we get a u squared. Great. Okay. Next, let's bring u to 1 over u. All right. So that's going to give us, let's see, if we bring u to 1 over u, we'll get natural log. Well, let's do the bounds of integration first. 1 over infinity, that's 0. 1 over 1 is 1. Natural log u becomes natural log of 1 over u. This becomes u to the negative 2. And our differential now becomes negative 1 over u squared du. And as you can see, we still have the same value. So that's valid. All right. Now, let's use the properties of logarithms. This is just going to be negative natural log u. All right, negative natural log u to the 4th. Well, that's just going to be natural log u to the 4th. All right, let's use this negative sign to switch our bounds of integration. 1 to 0. And then we'll bring in the u squared down below. So we'll just end up with u squared plus 1 again. All right. So now we have two expressions for I. We have this and this. All right, that means that 2i is going to be equal to this plus this. Sorry, plus this. And then dividing both sides by 2, we get that I is equal to the sum of these two integrals. And they have the same integrand, And they have, this one goes from 0 to 1, the next one goes from 1 to infinity. So we can combine them into one integral. Great. So there's our new expression for I. Next, we'll let some f of t be equal to the integral from 0 to infinity of x to the t over u squared plus, or we'll switch it back to x squared plus 1 dx. All right. And as you can see, this is going to be good between -1 and 1. All right. This implies if we take 4 derivatives of this using the Leibniz rule for differentiation under the integral sign, we'll get f quadruple prime of t is equal to the integral from 0 to infinity of x to the t natural log to the 4th x over x squared plus 1 dx. Okay, and this in turn implies that f quadruple prime at 0 is equal to I. All right, so now we need to find a new expression for this. And again, we are not going to be invoking the zeta function. If we were going to be doing that, I never would have combined these two integrals. I would have left it exactly like this. I'm sorry, I would have left it exactly as the sum of those two integrals before and brought one of them to 0 to 1. I would have brought the one that goes from 1 to infinity to 0 to 1. Okay. So anyway, we're going to continue from here. Let's find a new expression for f of t is equal to this. Well, we know this. We know that the integral from 0 to infinity of 1 over x to the t plus 1 dx is equal to pi over t times the sine of pi over t. All right. So now, just like in our last video, we need to somehow transform this into this. And I'm going to be doing the same thing I did last time. Instead of trying to figure out some u to plug in directly, I'm going to let x to the t dx be equal to du. So we're going to let x to the t dx equal du. This implies that x to the t plus 1 over t plus 1 is equal to u. And now we need to solve this for x. So we take the denominator here, t plus 1, and then we raise both sides to the 1 over t plus 1 power. So we get this. And you'll see, using the properties of exponents, the t plus 1 and 1 over t plus 1 will just turn into 1, and we'll just have x. All right. So now let's take our f of t and apply that substitution to it. Well, let's see. Do the bounds of integration change? Well, u is going to be infinity to the t plus 1 over... Oh, this should be t plus 1. I apologize. This is t plus 1. So no, the lower bound is not going to change, nor is the upper bound. Okay, so this part right here, x to the t dx, we defined to be du. That was the entire point of it. And now we need to square our value for x. So I'm just going to keep it simple for now. I'm going to erase that x, put a parentheses, and paste what our new x is. All right. And now our du. Oh, wait. No, that's it. That's the entire thing. Okay. So let's see if this matches up with our other f of t. So let's copy this down here and paste it here, and I will drag it over. And as you can see, they do in fact overlap. You can see these are the exact same function. All right. So now, what do we do? Don't forget, we only know this form. So we need to get that into this. We need to get this into that form. All right. So, how are we going to do that? Well, let's let W equal U times T plus 1. All right. So let's see. We can bring out this this exponent 1 over T plus 1 outside the parentheses to just give us 2 over T plus 1. All right, and now we're letting our W equal, well, let's let U, well, I'll show the entire thing. We want our W to equal U times T plus 1, because that way we can just get our variable of integration raised to a power, which is what we want. This implies that U is equal to W divided by T plus 1, which implies that du is equal to 1 over T plus 1 dw. So we'll perform that substitution. Again, our bounds of integration are not going to change. All right, so what do we have now? This becomes a W, and our du becomes a 1 over T plus 1 dw. Great. This can come right outside. And now we have the exact form that we want. Don't forget, we know this. So I'll copy that down there, delete it there. And this implies that this integral right here is just equal to this, where t is actually 2 over T plus 1. So put a parentheses there, 2 over T plus 1. And then again, we replace this with a 2 over T plus 1. And we'll bring this to the top. And we will bring this T plus 1 to the top, T plus 1. And we will leave it like that. Okay. So now we know that these two things are equal. So now we can say that f of t is equal to 1 over T plus 1 times this. And that allows for another cancellation. There we go. There's our f of t. Now, quote unquote, all we have to do is take 4 derivatives of this thing. Not an easy task, but completely doable for somebody with a knowledge of calculus BC. It would take a long time. I'm going to use an integral calculator to do this, and I will be right back. Sorry, I meant a derivative calculator. All right, so this is what we get. F quadruple prime of t is equal to this. I know, not fun, but at least you can see the entire thing on the screen there. So that is 4 derivatives of this with respect to t. All right. Well, so now we already know that our original integral I is f quadruple prime at 0. So I is equal to this, that's our f quadruple prime, at 0, at t is equal to 0. All right, let's notice something about this. This is a cosine function. If we let t equal 0, we get pi over 2 inside the cosine function. This whole thing becomes 0. And you'll notice the same exact thing is going to happen here because of this cosine. So this goes away, so that we skipped a lot of calculations. Now, this part right here, this is a sine function. We'll end up with sine pi over 2, which is just 1. So that part goes away. And again, this part goes away as well. Sorry, I made a mistake there. Let's go back. You'll notice in this part right here, I should have only deleted this. So that goes away, and this part goes away. So that's the answer. Okay, so that integral evaluates to 5 pi to the 5th over 32. All right, guys, hope you enjoyed that, and we'll see you next time.